Hello. For those watching online, I'm David, and this is a seminar on rearranging expressions. Last time I talked about rearranging calculations. Continue a little bit on that. I'll just remind you where I've been, and also talk a little bit about fractions and how they can be rearranged and calculated with. I will try and make sure that I get done everything I want to in that time. And when I talk about expressions, I mean algebra, things involving x's and y's and that sort of thing. My sharpener is not working.
I do need mine. I have one.
I've got it. Thank you, though. So last time I talked about the rules of being able to rearrange a calculation and not change what the answer comes to. And mathematicians are intensely interested in what rules go with that because it helps them to decide the rules of algebra. So the rules of algebra are not really anything different to the rules of how ordinary numbers work. And I spent some time talking about how you can rearrange expressions involving plus and minus and times and divide, and some that involve powers. And I'm just going to finish it off by talking about some things that involve division. So give me a second to find some numbers. So 8. That's not working, is it? Put magnets on them and they didn't work. They worked on my whiteboard. 2, 3. Nope, it'll have to be down there. Maybe this whiteboard's not magnetic. Nope. Alright, it'll have to be down here. Sorry about that. 3 times 4 divided by 6. Okay, so I talked a little bit about that. Last time, and about how you can rearrange things. And I talked about how if it's all times and divide, you can rearrange as long as the division sign stays with the thing that it was next to originally. So I can move all this over. See? I can move all that over and that will work just as well. 3 divided by 6 is a half. Half times 4 would be 2, and that would come to the same answer as it did before, whereas before it was 3 times 4, which is 12, and then divided by 6, which is 2, comes to the same answer. So, I talked about that. The problem is that mathematicians, when they do algebra, they very rarely write this division sign. You don't see it very often at all. And so we need a way of understanding how that division sign works for mathematicians, and that's to do with the fraction bar. So when a mathematician sees a fraction, they can understand it as a fraction, and they can also understand it as a division. So this division sign, no, it's just not going to work. This division sign is a picture of a fraction. I'm going to draw it bigger so that you can see and actually put the camera up. It's a picture of a fraction. This dot is representing a number that goes in this spot here, and this dot is representing a number that goes in this spot here. So when I write 4 divided by 6, I could think of it as 4/6. Okay, so the number before the division sign goes on the top, and the number after the division sign goes on the bottom. The division sign is a picture of a fraction. And that'll help you do things in a calculator, actually, because a calculator doesn't always have the ability to write fractions. Often, some calculators do have that ability, but it does mean that you can, even if it doesn't, you can do it. So if I go over to the document camera, and this is my calculator. It's a graphics calculator. I don't need one nearly that fancy. I could have used an ordinary calculator. And if I want to do 4/6, I can go 4 divided by 6. Now it will actually tell me what that is as a decimal, so I can use my calculator to convert between fractions and decimals. But I can do this thing here, 3 times 4 divided by 6, it will come out as 2. 3 divided by 6 times 4 still comes out as 2. But if there was an expression that did involve fractions, I can get my calculator to do it. So I'm just going to do some examples and show you what it looks like on the calculator. So if I see the number 1/2, it could just as easily be 1 divided by 2, with the idea that the number in that's not going to be able to see that. Let's try another colour. The number in front of the division sign goes on the top, and the number after the division sign goes on the bottom. And so I can ask the calculator what 1/2 is as a decimal, 1 divided by 2, and it tells me the answer is 0.5. Okay, I can also, that means I can do calculations that involve fraction bars. So if I see something that looks like this, okay, I can calculate what it is using my calculator, because I can use my fraction bar to be represented in my calculator as a division sign. The important thing to realise is that this fraction bar is holding together the things on the top and the bottom, so I need to put brackets in if I want my calculator to tell me what it is. So it's really the same as this. I'm going to need those brackets to get my calculator to do it. I'm just going to see if I can see them both at once. So if I want 3 times 5 plus 2 all over 1 minus 6 plus 8, I can say if I put the brackets around what's on the top and what's on the bottom, then it will come to the correct answer, 5.66667. So 5 2/3 apparently. But I can also use the rules of what I know about how to calculate things to calculate that myself if I want to. So I can see that the rules of which order you should do operations in say that brackets come first, and that includes brackets that are living inside, that are hidden because they're fractions. So it's not really brackets, it's grouping operation, grouping symbols, and the fractions group things together. So I can go 3 times 5 plus 2 over 1 minus 6 plus 8. Well, I can't actually do the division until I figure out what the top and the bottom are. So the 3 times on the top, times has to be done before plus, so I'll do that first. So the 3 times 5 has become a 15. And on the bottom, well, I can do the plus and the minus. I can do this plus 8 and this minus 6 in whichever order I want, as long as the 6 is still minus. So if you don't mind, I'm going to go the 1 plus 8 is going to be a 9. And the 15 plus 2 is actually 17. And the 9 minus 6 would be a 3. So that's what it is as a single fraction. It's 17 divided by 3. So let's just check to see if I've got that right. 17 divided by 3, same answer. Awesome. Now I could convert that to a mixed number and I'd have a much better answer of that. You know, 17 divided by 3, well, 15 divided by 3 would be 5, and there's 2 left over, so it's 5 and 2/3, which is why it's 5.66667. Okay, so that's how the order of operations interacts with the fraction bar, but there are a couple of other things that it's worth pointing out about the fraction bar. Okay, so I had planned for my things to stick to the whiteboard, but the magnet on this is not nearly as strong as it was back in my room, so I'm going to have to forego that and just write it on the paper. So back before we had a rule that said I can move times and divide around as long as the divide stays with the thing that it's divided by, and that applies to fractions too. So if it's all times and fractions, I can move my over something, I can move a denominator of a fraction anywhere as long as it's all times and fractions. And that's because putting something on the bottom of a fraction is the same as dividing it. Okay, and because I can do times and divide in any order as long as the divide still is still attached to the same thing, that means I can move things around anywhere and it won't change the answer. And this is the key idea of how a lot of fraction calculations work. So as an example, okay, that's 3/4 times 8/3. But you could just as easily read it as 3 divided by 4 times 8 divided by 3. Okay? So because this divided by, we've times by 3 at the beginning and we've divided by 3 at the end, they're actually not going to have a total effect on the actual answer. And so I can just as easily rearrange this way if I want and move the on 3 that was on the bottom here and the on 4 that was on the bottom here, and I can do my divisions in that order instead. So because it's all times and fractions, I can move anything on the bottom to anywhere else on the bottom and it'll be fine. So 3 divided by 3 is 1, and 8 divided by 4 is 2, so the answer is 2. Even without calculating that the answer was 2, I would know that it would be legitimate to move things around that way, even without calculating the answer. The whole point of this is that these calculations give the same answer even if you don't figure them out. Okay, so that's one way of dealing with it. The other way is to realise that if you have multiple things on the bottom of fractions and it's all times, you can times the tops and times the bottoms. And it works in both directions. So multiplication of fractions, remember that you multiply the tops and you multiply the bottoms. But what that means is that you can split things apart and move things around if you need to make it easier for you to do. Okay, so the multiplication of fractions says that I can multiply the tops and multiply the bottoms separately, and that will also be the correct answer. Like that, and that's the answer. But I also know that I can separate it out again after I've reordered things. So if I can go, well, 5 times 9, sorry, you know, times that's on the top, I can separate that all out. I can move it in a different order. That on the bottom, I can do that in whatever order I want. Look, 3 times 3 is 9. And I can separate it out again, you know, 5 times 10 over 8, that one and that one. Since it's all multiplication anyway, I can separate it into 2 fractions. And 9 over 9 is really 1. So I can move things around and switch things up and do any number of things and not change the answer. The reason why this is so important is that when we get to algebra, we don't always know what the numbers are. And so we might have to do this sort of playing around in order to calculate as much as we can without knowing what one of the numbers is. So 9 divided by 9 is 1, right? What a lot of people do when they're used to doing fractions is they notice that we could have done all of this if we wanted. We could have moved the 9 to the end eventually. We could have moved the 3's together eventually. And they notice that 3 times 3 is the same as 9. And they'll think, oh, well, eventually that's times 9 and divide by 9. And so I can cancel them out and not worry about them at all. And that's what the word cancelling out means for fractions. So a lot of people who are experienced with fractions will skip straight from here to this thing just here. Because they'll say, well, the 9 and the 3 times 3, timesing by 9 and then dividing by 3 and dividing by 3, that's the same. That doesn't really do anything, so I'm left with the 5 times 10 and the 8. The other thing that's important to know about fractions is that because you do multiply the top and multiply the bottom when you do these things, and also just because of how fractions behave, if you multiply both the top and bottom of a fraction by the same thing, the fraction stays the same. So if you multiply the top and bottom by the same number, it doesn't change the fraction. And that goes with dividing the top and bottom by the same number. And that's to do with how, you know, fractions work. A half is the same as 2 quarters, is the same as 3 sixths, is the same as 5 tenths. And so what's really happened there, if you just look at numerically what the numbers have done, you've just multiplied the top and bottom by the same thing. But remember that if it's all times and divide, you can multiply and divide anywhere. I know that if I multiply the top and bottom of that fraction by the same thing, it'll come to the same answer. So I could just as easily go, well, I'll just divide that by 3 and that by 3. The whole top and the whole bottom. But it's all times and divide, so that's okay. So I'll have the same as 5 times 10 times 3 over 3 times 8. And so the 9 divided by 3 is 3, the 3 divided by 3 is 1, and times 1 is not going to do anything. I can still divide the top and bottom by 3. Look, it's already times 3 on the top and times 3 on the bottom. I know that multiplying the top and bottom by the same thing doesn't change the answer, so it must be the same as 5 times 10 over 8. Oh, and look again, I can divide the 10 and the 8 both by 2, so it's the same as 5 times 4 over 5 times 5 over 2, which is 25 over 2, which is over 4. Which is a much easier number to understand than 50 over 8. So I can do that, but I could just as easily back here have done it the way I wanted and then said, oh, there's 2 goes into both of them, I'll just divide them both by 2 and it comes to the same answer. So that can be done at any point. You just need to be careful if there's pluses and minuses in your fraction. Because remember that what you're doing is you're taking the fraction as it's written and multiplying and dividing the top and the bottom. So something like that. Everything is a multiple of 3, so it would be not such a bad plan. I mean, what you really should do is you should add the top and add the bottom and then divide. But I'm thinking there's no particular reason I have to do that. I could, if I wanted to, if I really wanted to, I could take that and take what's there on the top and divide it by 3, and what's there on the bottom and divide it by 3 as well. And that won't change what the fraction is equal to, because I'm allowed to times the top and to times the bottom by whatever I want. The issue is, do remember that you're taking the entirety of what's there and dividing by 3. Now, if those things are all times and divide, it doesn't matter. But if it's plus, you've got to be careful. I still have to figure out what the top is before I divide by 3, unless I use the rule that says that I can bring a divide into a bracket with a plus. And I can bring a divide into a bracket with a plus. I mean, there's no reason for me to do this long way, except to show you that it's something that you could do if you wanted. Okay, most people when doing this would probably skip both of those steps and just divide everything on the top and everything on the bottom by 3. So my last thing about the way fractions rearrange will be to do with something like this. So I'm not quite sure how to say it. Something like that is the same as something like this. So basically the denominators of fractions can be cloned and spread out, copied across your pluses and your minuses as well. Okay, being copied across pluses. And that's what that means is this. It works one way or the other. So as an example, 6 plus 2 over 2 is the same as that. So this fraction, this over 2, because that's a plus, the over 2 can be separated across the plus. And that's just the same as me saying this. I can separate my divide by 2 can be brought in over the brackets. Same deal, my big divide by 2 can be brought in over the things on top. The time that you've seen this is when you're adding fractions. You've just seen it backwards. Five thirds minus 2/3. We can do it backwards. I mean, 5/3 minus 2/3 is 3/3. Okay, if you just say it aloud. But you can do it backwards to say, just a second, that on 3, they're both on 3. So I can write them both on 3. And so that's 3/3, which is 1. Oops, sorry. So mathematicians are really flexible with fractions. They will often treat them as if they are a division inside their head. Sometimes they'll treat them as fractions and times the top and bottom by separate things, in thinking of making equivalent fractions. Sometimes they'll actually do the division and figure out what the answer is, and sometimes they'll move the divisions in and out and around in order to calculate things. Actually, I do have one final way that mathematicians think about fractions, and that is the invert and multiply thing. So when you divide fractions, you're supposed to flip the one that you're dividing and times instead. And mathematicians think this way. Dividing by some number is the same as timesing by 1 over the number. Okay? And dividing by a fraction is the same as multiplying by the fraction but the other way up. So often they'll go a half times 4. Well, timesing by a half is the same as dividing by 2. This times a half is the same as this divided by 2. And they'll often think that way in order to help them figure out how to do a lot of these things. And that's precisely how the mathematician thinks about a lot of these moving and switching things. They don't really think of a divide by 2 as a divide by 2 at all. They think of it as a times by a half. And that's why it behaves the same as times does, because we know that multiplication like that, a mathematician will think of that as this. And they'll go, oh, well, that's okay, because I know that multiplication can be brought into brackets. Sorry. And they'll go back to it and go, well, 3 times a third, well, that's the same as dividing by 3, so 3 divided by 3 is 1. And 12 times a third, that's the same as dividing by 3, so that's 4. And this answer is actually like minus 3. A mathematician, even though that takes longer to do this calculation, that's how they think about it. And it's important to know that they do think that way, that dividing by a plain number is the same as multiplying by 1 over that number, multiplying by a fraction. So that's an insight into mathematicians' brains and how they think about moving and switching and changing things. Okay? And a mathematician will not always do things in the order they're presented. Sometimes they'll say, oh, it would be way easier if I just expanded these brackets, or it would be way easier if I just did that addition before that addition, or this times before that one over there. It'd be way easier if, oh, look, they've both got a 2 in them, maybe I'll draw them together. So just one final example of how a mathematician would behave when they saw a complex calculation. If mathematicians saw that, they'd probably go, oh, what is 8 times 6 again? I don't remember. But they won't bother too much about that, because they'll go, just a second, they've both got a 2. There's a 2 inside that 8. Actually, there's a 2 inside that 6 as well, but I'll just remove one of them. They'll think this, they won't write it. And they'll go, look, now they've both got a 2 times. And I know the rules was that if there was a bracket, it would be the same as this, because I can bring a 2 times inside a bracket. And then they'll go, oh, sweet, like, so that's the same as 2 times 5 plus 24, which is the same as 2 times 29. And then they'll go, oh, I don't know how to figure out 2 times 29. And then they'll go, oh, but 2 times 30, that's not that hard. So this is actually the same as 2 times 30 minus 1. And I can do that. Two times 30 is 60. Sorry, I'm going to go up to the top of the page here. I don't want to go over to the next page, so I'm just going to put an arrow and go back to here. 2 times 30 is 60, and 2 times 1 is 2. 60 minus 2 is 58. Now, you could say to them, right, surely it would have been quicker to just go 2 times 5 is 10, and 8 times 6 is 48, and 10 plus 48 is 58. Sure, if they had happened to know off the top of their head what 8 times 6 is. But if they didn't happen to know, but they did happen to know that 8 was 2 times 4, they'd start shifting things around and moving things around in order to try and figure it out from the information that they did know. So mathematicians are actually usually not very good at remembering their times tables. Okay? They might not know what 8 times 6 is, but they might happen to know some other information, and they could still figure it out anyway because they know the rules of how mathematics works. So there's an insight into the mind of a mathematician. And this is the key to how algebra works. Algebra is worse than this. It's not just that you don't know what 8 times 6 comes out to, you don't even know what one of the numbers is. So, I mean, this is important, and I will use my whiteboard for it. Just give me a second, I'll find the appropriate numbers. Is that a plus? Come on, got to be a plus in here. So we had 2 times 5 plus 8 times 6. And that was all great, but we couldn't remember what 8 times 6 was, and so we had to find a different way of calculating it. In algebra, often it's not that you don't remember what the answer is, you just don't know what the number is at all. It's an unknown number. It's not just a 6, it's a number that I don't know. And what we do is to hold a place for it so we don't have to keep saying it's a number I don't know, we give it a letter. The traditional letter that people use is X. But there's nothing to stop you using an A or a B or a W or a Greek letter like rho or alpha or something. We now have a number and we don't know what it is. And so that really severely restricts our ability to calculate stuff. But mathematicians, never to be dismayed, will say, well, I'll calculate as much as I can before I can do anything. Okay, and I might try and factorize it, as in bring things outside of brackets to try and get it to a stage where I can say something about this answer, even if I don't know what the number even is. Okay, so this is when we get into algebra, and this is called an expression, some sort of calculation that is involving well, it could just involve plain numbers, but some sort of calculation that usually involves a letter is called an expression. And I will write that down because that needs to be explicit. An expression, that's actually not 2 words, that's only 1 word. An expression possibly involving letters. But the important part of an expression is it doesn't have an equal sign in it. It's just some times's, some divides, some brackets, some powers, some x's. Okay? And you should know that the proper word for those letters that are standing in place of numbers is pronumerals. It's a bit like pronouns in grammar, but a letter in place of a number is called a pronumeral. In the one that I had before, that X was standing in place of the number 6. But theoretically we don't know what number it stands in for. And sometimes a letter can stand in for any number of other numbers. It doesn't have to be a specific single number. It could be representing all possible numbers as well. So a letter, a pronumeral, doesn't have to be a single number. It might be a single number, but it could also be trying to represent all possible numbers at the same time. Okay? the rules for rearranging expressions are the same as those for rearranging calculations with numbers. So just a second. So same as for number calculations. That's the big point I want to make. I spent a lot of time doing it with plain numbers, but all of the things I have mentioned will work exactly the same if there's letters in those places as well. And the reason they work the same is because the letters are just numbers. We just happen to not know what the numbers are at the moment. Okay? So often, people who are familiar with algebra, even if they know what the numbers are, they will actually do some rearranging with the calculations, do some rearranging with the letters, and just put the numbers in at the last minute because it's easier for them to think in terms of letters than in terms of numbers. Okay? People who are first learning, it might be easier to replace that letter with a number and see what happens to it as you move along and follow the number, so that you can get a feel for the fact that it really is just a letter. There is one major difference though in how mathematicians write when they're using letters, and that is that they will tend not to put time signs in unless they absolutely have to. And things that are just next to each other are assumed to be multiplied. So just note. Things next to each other are multiplied. Now, plain numbers, you'll have to put a time sign in, because if you put a 2 and then a 5, like this, wait for the camera to sort itself out. If I do that, then it's the number 25. So I will leave the time sign in there so that my readers can tell that it's actually the number 25, actually number 2 times 5 and not 25. But over here, I will remove that time sign and just call it 8x, under the assumption that because it's a letter, people will assume that without any sign between them, an assumption is that it's 8 times x. One of the reasons that they do that is because if you think about it, you could say this as not 2 times 5, but 2 5s. And so we're reading this as 8 x's. But we don't say 8x's, we just say 8x. So all of the rules for how you're allowed to rearrange numbers apply perfectly well for rearranging letters as well. And the reason we want to rearrange letters is to make the calculation look as simple as possible, so that at some future time when we find out what the x is, it will be easier to figure out what the answer is. Or it may be that we have a particular purpose in mind. So I'm just going to do some examples to just show some of how this rearranging with x's and y's works. Okay? So remember, I'm just putting it in explicitly with the times as 8 times x and plus 2 times x. There is some unknown number x. It could be trying to represent all possible numbers. It could be representing a particular number that I don't yet know. But for the moment, it's just a number that I don't know, and I'm going to treat it as if it was a number. I know that this would be way simpler if there was only one x on the page, because the less times the x appears in my calculation, the less chance I will have of getting the answer wrong at the end. And I know one of the things that mathematicians will write it like that without the time signs. But I know that the time signs are really there, okay? I know that this could have come from doing this. I'm going to remove this line and put it back in a second. So this 8 times x and this 2 times x could have come from expanding out this bracket. So if I work this backwards, I know that a times can be brought inside a bracket with a plus. So this could just as easily have come from, I could just do that backwards, right? I can pull the x out, and now 8 plus 2 is 10. So even though I don't know what x is, I can turn 8 times x plus 2 times x into 10 times x because of the rules of how numbers work. When a mathematician writes this, it will be much more like 8x plus 2x. And they will skip straight to this step. They won't put the bit in between. Okay? That's one of the reasons to write it without the times signs, because if you think about it, 8x's plus 2x's is 10x's. That's how they actually say it in their head. But what's really going on is we're working backwards on the rules that we know about how numbers work. Okay, this is just a random example. X plus 1 squared minus 3x. Okay, there's 2 x's here. They're the same letter, so they represent the same number. I just don't know what that number is. And I need to try and figure out if there's a better way of writing this that's easier to write. Now, I just think about what's allowed. If these were numbers, if I had 7 plus 1 squared, the normal rules of ordering things would say that I'm supposed to be figuring out what's in the brackets before I do the squared, but I don't know what x is, so I can't figure out the brackets. So there must be some other way of writing this so that it's easier to do. What else can I do? Well, if that was a times 2, I'd be able to bring it inside my bracket. But powers don't come in over plus, because if you recall last time, there's plus and minus down the bottom, times and divide here, powers and roots is the next level, and they only come in over the next one down. If it was x times 1, it'd be sweet. I could bring the squared into them separately, but it's an x plus 1, so I can't. Okay, so what do I do? Well, I could leave it like that. I could say, I give up. There's nothing else I can do. But I could instead try and think about what squared means and go, just a second, this is the same as saying squared means times by itself. 5 squared is 5 times 5, 7 squared is 7 times 7, 2 squared is 2 times 2, x plus 1 squared must be x plus 1 times x plus 1. Whatever this number is, whatever x plus 1 works out to be, if I was going to square it, I'd be timesing it by itself. So I could write it like that. Admittedly, that doesn't look any simpler, but at least it's a different way of writing it so I can understand this in a different, I try and understand it better. Now what you're supposed to do, now I do know something else, there's really a times sign just here. So I could go this times that and this times that separately. Okay, so I could do this. All of that can be brought in here because it's really a times. And I haven't done anything to the 3x, so it's still there. It's still looking way more complicated. But can't I do the same trick again? This one can be brought in here. And look, times 1 is the same as just not doing anything. So x times x is the same as x squared. 1 times x is x. X plus 1, anything times 1 is the same as what it was before. Now, just let me check. All of this came from that one there. And this came from that one there. It's important to just check to see if they belong together. Okay, no, it's all good. So now it's all just plus and minus, right? I've got an x squared, I've got an x plus an x, and a plus 1 and a minus 3x. My rules of maths say I can do plussing and minusing, I can rearrange anything that's involving just plus and minus in whatever order I want, as long as the things that are multiplied stay together, the things that are minus, the minus still belongs to them, and the things that have powers on them, the powers come with them. So I know that I can say, well, this bit and this bit and this bit, well, they can all be brought together. I can go, well, what's x plus x minus 3x? Well, one might remember what they're thinking about. X and another x would be 2x's, minus 3x's would be, just a second, it's a little easier to do it this way. So the x plus x, well, that's 2x's, right? In the same way that 3 plus 3 would be 2 times 3, 5 plus 5 would be 2 times 5, 7 plus 7 would be 2 times 7. And remember that I can do this trick back here backwards if I want. Those two x's can come out and become 1x. All right, one final trick. Well, plus minus 1 is the same as just minus 1. I don't think I mentioned that in any of the early ones. But just a second, 1 times x is the same as x. Now that was the long way. A person experienced in mathematics and who's been doing this for years would skip most of those steps. And they're able to fluidly just add things together without explicitly using this rule. So if you want to get really fast at algebra, it's really important to just get used to that rule of combining things together when it's just 4x and 1x and 7x and stuff like that. So I can go (2x) and 3x would be 5x, minus an x would be 4x. And they just get used to just pulling things together like that. And they also get used to just dealing with the negative numbers coming out when they have answers. 5x minus 8x, well, 5 minus 8 would be minus 3, so it must be minus 3x. And so the x's just sort of get carried along for the ride. But what's really going on is that I've got a 2 and a 3 and minus 1x. Okay, that's what's really going on. That's an alternative way of dealing with the same problem. I guess the point I'm trying to make is that it's all just algebra. It's all just the rules of numbers. So it can take some practice to get used to it, and I would really recommend looking up the Khan Academy. It has heaps of practice. But it's really just based on the rules of how numbers work. You can rearrange numbers in that way and get the same answer, and so you can rearrange calculations in that same way, letters in that same way and get the same answer. One more. This one looks really scary. It's a fraction within a fraction. 1 over 1 plus 1 over x. Okay? That's really a scary looking thing. Okay, but there should be ways of making it look less scary and calculating something different. So I'm just showing you some of the ways that people work on these things. I can't cover everything. What can I do? Well, there are lots of ways of thinking about it. I could look at just this bit and see if I could figure out a way of dealing with that. Maybe let's try that. Well, if that was 1 plus 1 over 2, it would be 1 1/2. Okay? 1 plus 1 over 3 would be 1 1/3. And it should conceivably be possible to turn those into proper fractions, right? Mixed numbers like 1.5 can be turned into fractions like 3/2. So I should technically be able to rewrite that as something over x. And that's my thinking. I'm going to think, well, it's just numbers. What would I do if it was a number? What would I do if x was, say, 2? And I would attempt to rewrite it as a single fraction. And I know that the best way to add fractions is to make the bottoms the same. So 1 can be rewritten as 2/2 and 3/3 and 5/5 and 7/7. They're all equal to 1. Even better, it'd be so much easier to rewrite my 1 as x over x. Because that's what 1 is. And then I could think, just a second, I know the rules. This is just x divided by x and 1 divided by x. I know that divided bys can be brought in and out of plus. So I can do this. These two on x's have come together to be this on big on x. And I know that that rule works as long as there's a plus there. If it was a times there, I would have done something entirely differently. I would have times the tops and times the bottom. And so now I have that 1 plus 1 over x is that. And that's great, except that's not what I was actually looking for. I was looking for 1 over 1 plus 1 over x. But just a second, isn't that the same? So this 1 plus 1 over x, I can replace by all of that. And I put it inside a bracket to remind myself that all of this has been replaced by all of that. But just a second, a big fraction bar. Fraction bars are really just division signs, aren't they? This big fraction bar here, the thing on the top goes to the left, the thing on the bottom goes to the right. It's just a division sign. So I'm now using the idea that fraction bars are really just division signs. And then I'm going to use the rule, just a second, dividing by a fraction is the same. So this dividing by a fraction is the same as timesing by the fraction up the other way. Because that's the rules for dividing by fractions. It doesn't matter whether they have letters in them or not. I know that if I divided by 2/3, it would come out to timesing by 3/2. And look, 1 times any number is always that number. 1 timesing by 1 doesn't do anything at all. So this comes out to the answer of x over x plus 1, which is much less scary than the thing that I started with. So I'm hoping that those listening and friends here in the audience are understanding that it's just the rules of numbers. If you can go back and say, just a second, what would I do if it was an ordinary fraction that didn't have strange letters in it? What would I do then? I'm going to do this one in one different way and then I'll stop. Another way of thinking about this one is to think, just a second, what's the most annoying thing about what I've written here? You know, the fact that it's the not knowing what the x really is that's causing my pain here. And it's the fact that the x is on the bottom. If it was 1 plus x there, I wouldn't be able to do anything. If it's 1 over 1 plus x, there'd be nothing I could do. Okay, because I know that division doesn't separate on the top of things, it only separates on the bottom. So I couldn't spread the 1 over separately across that plus because it doesn't do that when it's on the top. So it's the x that's on the bottom that's the problem. But I also know that I am allowed to multiply the top and bottom of the fraction by whatever I want and it won't change the answer. So I could times them both by x. Why would I want to do that? Well, I'll show you why I would want to do that. So 1 times x on the top is really x. And the rules for multiplying say that I can bring times's inside of pluses, inside of brackets with plus. So 1 times x is x. We'll just write them explicitly. And I'll get that. Awesome. 1 times x is just x. Wait just a minute. 1 over x times x is the same as 1 divided by x times x. And I know that timesing by 1 over x is totally the same as just dividing by x. Okay, because I know that timesing by a half is the same as dividing by 2. So this is the same as x divided by x. And I know what x divided by x is. It's 1. Anything divided by itself is always 1. And so that's a different way of getting the same answer. I guess the point I'm trying to make is that there's no one perfect way of doing algebra. As long as everything that you do along the way is a legitimate thing to do, you can do any of it. And you'll often get to the same place. Or you'll get to something that looks slightly different. It's okay if it looks different as long as you're satisfied with how simple it is. Next week, well, in 3 weeks' time after the holidays, when I talk about solving equations, there will be more of me doing these calculation shifty rearranging things with x's and other letters. And my hope is that as you see me explicitly saying the rules that I'm using, it'll become easier to see what's going on. One of the problems with algebra, it's very difficult to learn straight up as algebra. It's much easier to learn while you're trying to do the next thing. So if you do want to learn more algebra, I would recommend looking up algebra and expressions online. I reckon the Khan Academy would be a great idea. He has, Selmat Khan and his team have put a whole lot of stuff online to help with learning algebra. I'm just trying to find where I just put my pen. So. If you search for that online, you'll get lots of exercises. Also, any high school textbook from about year 9 will contain this sort of thing. And there'll be plenty of exercises that you can practice on to get used to doing some of these things. But I will say that you can always come to the Maths Learning Centre. We've got some textbooks on the shelf and you can have a look at them too. But any textbook that is from about year 9 or above will contain this sort of stuff that you can practice on and get good at. But in general, often just coming to talk to someone to say, look, I'm not sure what's going on here, and having someone explain to you their explicit thought processes, you'll get better at the algebra as you go. Well, have a nice break. And I will be back after the break to talk about solving equations.